I'm Nicholas Geller, and this is my Physics 2211 Lab 2, which is projectile motion. My table of contents, so first I'll have an intro where I'll go over any concepts and equations that I'll be using during my experiment. Next, I will show my experimental data, which was gathered using Tracker, my GlowScript computational data, my results and analysis, and then any discussion questions. So for this experiment, the objective was to analyze the position versus time graphs of a real-world tracker using the Tracker app, and then using GlowScript computational models to look at the same scenario. And with the GlowScript computational model, I was looking at the scenario with and without drag. I'm using this experiment in order to test the principles of motion. The fundamental principles of motion that I'm using for this experiment are Newton's second law, which is F equals ma, the position and velocity update formula, gravitational force in terms of acceleration due to gravity, and drag force. And it is important to note that if there is no drag force in a projectile motion, that the F net is equal to the force of gravity. So this is my tracker data and video. So for this lab, we threw a paper ball in the air. The time between each time interval was about 0.033 seconds. The data shown on the right is the axis position versus time graph in both the x and the y direction. The top one is the x direction, the bottom one is the y direction, and the bottom table is all of my data. Next was my computational model, where some assumptions we have to make is that gravity and drag are the only forces that are acting on the system, and that tracking markers were placed completely accurately every time when I was going through using the Tracker app. This is my GlowScript code that I used to predict the motion of an object in a similar scenario to my physical scenario. So the code on the left is without drag, where F net is just equal to the force of gravity. And the code on the right is my GlowScript code with drag, where drag is factored into the equation for F net. When I put this code through GlowScript, I got these results showing that these are all my graphs for gravity with no drag in it. And then on the right, these are my graphs for projectile motion with gravity and drag force. This is my final graph showing all three curves. You can see on with the red dotted line, that is what my Tracker app predicted for the projectile motion. You can see it's a lot flatter than the other two, whereas in Tracker it had the ball going below the y-axis, so you can see that it's a lot more gradual, and the drag force has a lot steeper decline at the beginning and then levels out at the end. What does it mean? So none of my predicted models showed a demonstration of terminal velocity, as the object did not have enough time to fall. If I wanted to conduct an experiment to demonstrate terminal velocity, I would have to throw a ball at a much greater height to allow for drag to build up and equal the force of gravity in order to allow for a constant velocity. So for this experiment, I could drop the ball from a tall building or some other type of plane/drone. Now for my what-if statement, I'm evaluating if the object were initially thrown straight up with the same initial speed as my original experiment, would the time for the object to reach the ground be the same? I said that the time of the object to reach the ground would be longer from the same initial point of release. This is because the vertical path of displacement would be larger, and the object would have to decelerate in the y direction back down to zero before it started coming back towards the ground. So the equations I used to evaluate this were the kinematic equations, where the time to reach the peak would equal the initial velocity divided by the acceleration of gravity, and my time to reach the ground would be the same thing. It would be the velocity at the top divided by gravity. So you add those together for a time total, and you get to v initial divided by g, which is larger than the velocity for the whole process in my original scenario.